Everybody, these are going to be your notes for types of mixtures. So you should have your Unit 2 packet out and open to page 20. You'll be taking these notes on Wednesday on your Cyber Day, so you should be ready to hop right into this on Thursday. So pause the video if you need to take a second to get your Unit 2 packet out, and here we go. So first type of mixture we're going to talk about is a solution. Right? Solutions are true homogeneous mixtures. So these are the ones that, right, they look uniform throughout and they are uniform throughout. A good example of this might be something like Kool-Aid, right? When you look at Kool-Aid, it's just a red liquid the whole way from top to bottom. If you take out like a magnifying glass or a microscope, you're not going to see particles in it, and that's because the sugars from the Kool-Aid have dissolved into the liquid. So all particles are broken down into individual molecules or ions when we put them in the liquid, and this is a term that we call dissolving. All right, so here is a little nano view of what's happening when a substance dissolves. And it all depends on our substance, whether it's going to break down into its ions, which are the individual charged atoms of the molecule for something like salt, or whether it will break down into its molecules for covalent compounds. And we'll talk about ionic and covalent compounds when we get into Unit 3. So let's take a look here. When we have a grain of salt, right, it's in this nice fixed pattern, right? We put it into our liquid water, okay, stir it up just like he's doing with his hand. And what's going to happen is all of the individual pieces are going to spread out. And that's why our solutions look to be and are homogeneous, right? All of the individual, the sodium ions are the red dots, the chloride ions are the blue dots, and they're separating into their individual pieces. When we have something like sugar, it also dissolves. It just dissolves a little bit differently. So you put a clump of sugar in water, right? And what's going to happen is that clump is going to break down into its individual molecules. So not into its ions, but into its molecules. Now, these molecules are going to be significantly smaller than they look in this video, right? Molecules are about 1 billion times smaller than what we would see with our eyes. So we would not be able to see these either, even under a microscope. Right? That's why we say these are truly homogeneous mixtures. Alrighty, so back to our notes. All right, and since these molecules and ions are so incredibly small when we dissolve them, a beam of light will pass right through. So we won't be able to see the path of a laser beam, right? And this will make more sense when we talk about colloids. But if we shine a laser pointer through this, right, all we would see would be the dot on the other side, right? We wouldn't be able to see the path of the laser throughout. And that's because those particles are not large enough, right, to disperse the light. All righty, so a little bit more on solutions. Solution is made up of substances called solutes, which are dissolved by the solvent. So remember that video we just watched? Our solute would have been the salt and the sugar, and our solvent would have been the water. I would definitely star this point right here. It's important you will definitely be quizzed and tested on this. It's something that students often mix up. Let's see here. Water is commonly used a lot as our solvent, and that's why we call it the universal solvent. It does a great job for dissolving things, right? And this is probably why maybe you soak dishes that might have some hard food stuck to them, so it can dissolve some of the salts and sugars and other atoms and molecules that might be clinging to the whether it's silverware or bowl or plate or whatever it might be. And some examples of solutions, we have soda, iced tea, lemonade, any sort of salt or sugar water, because those are things that will dissolve. And you can notice these all will look uniform throughout. Now, if we're including the ice, as part of our mixture here, then this would not be classified as a solution because the ice, does not allow it to look uniform throughout. So that would make it a suspension, which we'll talk about in a little bit. All right, next one we have here, and this is the first of our two heterogeneous mixtures, is a colloid. So colloids will look to be homogeneous from your naked eye, but under further examination through a microscope, we can see that they truly are not heterogeneous, and we can see the individual pieces. It's not uniform throughout. All right, so what happens here is that it breaks down into small clumps of molecules. but not into individual molecules like we did with the solution when the solute dissolves. Trying to go back here. Having some technical difficulties, bear with me. Alrighty, so these particle sizes that are breaking down in the colloid are very small, between 5 and 200 nanometers. Again, super small, so small we can't see them with the eye or microscope, but we do know that they are not fully dissolving. Some examples of colloids would be things like mayonnaise, jello, fog, butter, whipped cream, right? These things all look to be homogeneous throughout, but we know they are not. Right? And we were talking about the laser pointer with solutions, and you're probably wondering, why are we talking about laser pointers? Well, it's because of our colloids, and colloids display what's called the Tyndall effect. So this is how we know those particles have not fully dissolved, and we do not have a true homogeneous solution, because we can see a beam of light scatter as we pass through it. Right? So if we shined a laser pointer through this jar of milk, right? You might have to be close to the edge or maybe water down the milk a little bit, but you would be able to see the path of the laser go through the glass. Right? So here's a funny video of the guys from Big Bang Theory, right, using the Tyndall effect to play a very complicated version of chess. So I don't think you'll be able to hear the sound, so I'm not going to imitate the weird sounds that they make. Get through the commercial quick, and here we go. All right, so their weird game, they're playing this weird game of chess where it involves having to go through. So what he's doing is spraying a little bit of dust and air, some very small particles, creating a colloid mixture in the air around him, and that allows the laser pointers to be seen. Right? You've probably seen this in spy movies as well. Maybe you've watched like Ocean's 11, or I think like Spy Kids was a movie growing up when I was growing up that involved these lasers, right? And he crossed one of the lasers and let them know that he failed whatever challenge they had. Right? But that's a good example of a Tyndall effect. And we have some other ones. Right? So here's what it might look like as we shine a laser pointer right through a colloid. Right? We can see the path of the laser. Our air mixture is not a colloid, so we cannot see the laser pointer, but when we get to the liquid, we can. Right? So here's an example of somebody shining a laser pointer through a solution and then through a colloid. Right? We cannot see the laser path through the solution, but we can through the colloid. Right? And that's because the clumps are significantly larger and they will disperse that light. Alrighty. Another good example of this, if you've ever been like watching TV when it's sunny outside and a beam of light's kind of coming through your window and you see all these things floating around, like little pieces of dust and hair and stuff like that. That's an example of the air mixture in your living room or wherever you're watching the TV being a colloid, right? That's why you can see that gleam of light. Also, that's the reason why at concerts they use smoke machines, right? It's not because the smoke makes it look cool or they're trying to make it tough for you to breathe, but if you didn't have a colloid mixture in the air, you would not be able to see the laser show that they paid a lot of money for. All right, and our last type of mixture, and this is another heterogeneous mixture. This is a, you can see that it's heterogeneous with your eyes, much easier to see than a colloid, and that is a suspension. So in a suspension, your particles are large enough to be separated by a filter. So we could use whether it's a strainer in your kitchen or actual lab filter paper in the chemistry lab, we can separate the liquid from the solids here. Right? When you leave these sitting out, the large particles will fall to the bottom. Right? And that's because typically solids are the most dense form of matter for a substance. Now, it's not like the liquid and solid are the same throughout, so there are some complications there, but solids typically will fall to the bottom. And some good examples would be paint, right? That's why we need to put the paint in that super shaking machine at Lowe's or Home Depot before you take it home so that you're getting rid of those clumps. Or if maybe you have Italian salad dressing, you have to shake it up first before you put it on your salad or whatever else you're putting it on. Alrighty. Here we go. So here's a little... Alrighty, I'll have to find this on YouTube. So iron and sulfur. All right, so we can see that when we combine things like iron and sulfur, right? If we combine the two as a mixture, right, very easy to separate, and we can see that the iron would still maintain the same properties and be magnetic. Okay, so we have iron on the left, we have sulfur here on the right. Right, sulfur is that yellow-looking element that smells like rotten eggs. Iron is dark. I'm sure you've seen iron filings before. Maybe you've played that game at the doctor's office where there's like a magnet underneath and you can move the cars around. Maybe you've used like an Etch-a-Sketch, right, that uses iron as well. So we mix these two together, right, we can separate it pretty easily with the magnet. Right? You might want to take note of, right, her technique here, having something over top of the magnet so it would be easy to get off the magnet if we ever wanted to find the mass of that substance. Hint, hint, wink, wink, you might want to know that later. Right? So the physical mixture, right, did not change the properties of our original elements. Okay, but when we chemically combine iron and sulfur, so when we chemically combine iron and sulfur, right, sorry, I had to go back a little bit. Right, our properties have changed. So we'll end up with, right, she heated up this with a Bunsen burner, right? You can see your sulfur element here, your iron element here. Combine the two, right? We get this dark, solid, spherical mass right here. Now, originally, only the iron was magnetic, okay? But when this, right, teacher takes a magnet to this piece of iron sulfide, right, our properties have changed. Okay, so let's see what happens here. So we are able to pick up the entire substance, right? So it's no longer just iron, it's no longer just sulfur, right? It's not the two mixed together and packed very tight and we're just holding on to it because the iron's there, right? We now have iron sulfide, and that changes our properties, right? The sulfur before was not magnetic, but now iron sulfide is. Alrighty. That is the end of the notes video for today. Hope you enjoyed the video. No Edpuzzle this time. You're welcome. See ya.